Hi, in this tutorial I'm going to talk about the essential matrix and the fundamental matrix in computer vision, how to find them and the properties. So essential matrix and the fundamental matrix. But before we start, let's review some stuff together to see if we're on the same page. Okay, imagine we have two cameras. This is my first camera. It's the image plane of the first camera. And this is my second camera. And this is the optical center of the camera on the left, and this is the optical center of the camera on the right. And this is a point in arbitrary point in the world. I denoted with capital P. Okay, so the rays of the light from the point P will go through the optical center in the first camera and hit the camera image plane in this point, for instance. And also they will go through the second camera and hit them in a point like this. So when we look at this camera, when we look at the image plane, we can't say for sure if this point was actually here, and call them P1, P2, P3. We can't say for sure if it was here, or here. Because we lost one dimension. So this point could be on any of them. And if I project them, I will get another point here in this in the second camera plane. So let's just review the names. This line that connect these two optical center is called baseline. And the point that this line hit the image plane is called epipole. And as you can see, these ray of lights, which go through P2, P3, and PM, which could be any of this point from this line, they will form a line in this camera. So for this point P, we have a line which is associated with that and the second camera, because we don't know where is the line, where is the point exactly on this line, and for every point on this line we'll get a point here, which eventually they will form a line. And always one side of this line will go through the epipole. You can see geometrically, if I choose another point here, eventually one side of the line will go through this point, which is called epipole. So this is some geometrical constraint. Later on we will visit that algebraically, and we will see that this constraint is true also algebraically. Okay, so this is called epipole. This is called epipolar line. For point P, and this plane will be called epipolar plane. If I move the P up and down, I will get another plane, but it always go through this epipoles. Okay, that's the first thing that we need to review. The other thing is the equation of line in 2D is something like ax plus by plus c is equal to 0. I can rewrite it as a, b, c multiplied by x, y, 1 equal to 0. So this can be seen, this A, B, and C can be seen as they are the component of the unit vector in the direction of normal between the origin and the line. And every point on that line, when it's dotted with that, has a distance d from the origin. For instance, if you have a line x equal to y, you can write it x minus 1 equal to 0. This is a line, and a and b are 1 and minus 1, so this is going to be the unit vector. And so I can write it down like n of x, n of y, and minus d. So here this a and b, c could be seen as the this vector a and b, 1 and minus 1, and the distance from origin is 0, which is minus d. So we are looking for some duality between line and point, because you can see here we have lost one dimensionality, one dimension. Here we had a line, and here we had a point. So there's a duality between line and points in the real world and in the image plane. Okay, the other thing that we need to review before going further is this notation is the cross product. Okay, the cross product between every two vectors is 0. This is something is pretty simple. And the cross product between one vector and the other vector can be written as in a matrix form with this notation. So here we have two vectors, and this is a cross product, and here we have a matrix A, which is something like this: 0 minus A3, A2, A3, 0 minus A1, minus A2, A1, 0, multiplied by B1, B2, B3. So I just turned the cross product into a matrix multiplication. If you do the cross product, you will see exactly the same result. And the rank of this matrix is 2. This is something we have to remember. We're going to need it soon. What is the rank of the matrix? Rank of matrix is the maximum number of independent rows or columns. And 4 by 3 by 3 is at most 3. And here the rank of this matrix is 2. And if you multiply this matrix by any other matrix, the rank is going to be the new rank of the new matrix is going to be 2 again, because it's always the smallest rank. Okay, now we're ready to talk about the essential matrix. So essential matrix is a matrix that relates two cameras. The points of the frame of two cameras together. For instance, if this is your first camera and this is your second camera, and this is the optical center, we're looking for a matrix that relates this frame, which represent the camera frame in one, the right camera to the left camera. So if this is, if I call this frame XL and this one XR, we know that for any two frames in 3D, we can translate and we can transform one frame to another one by rotation and translation. So X of L is equal to 3 by 3 rotation multiplied by XR plus T. So if I cross product both sides by T, I will get XL T cross product R XR plus T multiplied by T, and I just said this is 0. Okay, now if I dot product both sides by XL, XR. So the result of this cross product is a vector which is perpendicular to the both, to the XL and T. And if I multiply dot product by XL, which is perpendicular to that, the result gonna be 0. So this side gonna be 0, and this side gonna be I can write this dot product as a matrix just by and here I can again turn this cross product matrix operation that I just introduced earlier in the previous page. Okay, so I can this is 3 by 3 matrix now of rank 2. This is 3 by 3, and these are two points 3 by 1. So I can call this E and rewrite it as this X of L multiplied by E X R transpose, sorry. So this is the definition of essential matrix, but as you can see, relates the frame of right camera to the left camera. So that was the essential matrix. Now we are introducing fundamental matrix. Fundamental matrix is a matrix that relates something in the image plane from one camera to another camera. Okay, so let's write fundamental matrix. Okay, we know that if you have a point in world coordinate system like X, Y, Z, and W, if I multiply it by 4 by 4 matrix, which translate the point, transform the point from the world coordinate to the camera coordinate, I can get the point in camera coordinate. So it's going to rotation and translation. This will give me the this is P in world coordinate, and this is simply 4 by 4 translation, which give me the point in the camera frame. And if I multiply this by intrinsic matrix, I will get the point on the on the image plane based on the pixel. And you remember it was f of s multiplied by here we had origin in the origin of x, origin of y, and here we have f over s, which basically give me how many pixel per meter or per millimeter that I have. F of y over s, and here was the skew parameter, which for modern camera we usually put it 0, and the rest is again 0. So if I have a point in world coordinate, this will give me the camera coordinate, and this will give me in the pixel base in a unit of pixel on the image plane. Okay, so I can write down the point in the image plane is equal to k, which I this guy, and multiplication of this by this point in the world coordinate multiplied by this 4x4 matrix is a point in the camera coordinate. So I can write the inverse, and I can write it like point in camera is equal to k minus 1 in the image plane, p image. Okay, so 1 point in the camera coordinate is equal to k inverse multiplied by point in the image plane. So if I just plug this p for right and left, I will get k minus 1 p. Okay, for the left, I'll just put the L here because the camera might not be exactly identical. P of image for the left, transpose multiplied by essential matrix multiplied by k of right, intrinsic matrix for the right camera, multiplied by point of image plane in the right equal to 0. So if I just extend this transpose, you know that for two matrix it's going to be from right to left, so it's going to be point in the left image, k inverse in the L, e kr inverse, and pr is equal to 0. So I can rename this as f and call it, sorry, I have a t here because here we had a transpose, pl transpose multiplied by f multiplied by point in the right camera equal to 0. So this is a fundamental matrix which relates something from the left image plane to the right image plane, and the essential matrix was relating basically these two frames to each other. Okay, so now let's see how can we find the fundamental matrix. Earlier I said this operator has rank 2, and basically our fundamental matrix has a rank 2 here. It's a 3x3 matrix, but it has a rank 2. So if I want to write it down, it's something like this. F1 1, F1 2, F1 3, F2 1. So basically, for one given point, if I write the this equation, it's going to be u v1 multiplied by this is 3 by 3, or sorry, it should be 3 by 1. Sorry, 1 by 3. U v1 multiplied by f multiplied by corresponding point u prime 1 is equal to 0. So now we're looking for this f, which is 3 by 3 and has a rank 2. We can divide everything by f33. So it just give for scaling. So we have actually 8 unknowns. So if I find the equation for 8 unknown points and rewrite it, I will get a big matrix like this. U print 1 U 1 U print 1 V 1. I'm just multiplying this by this, this by this, and this by this, and then by this, and rewrite the equation. U print 1 V print 1 U 1 V print 1 V 1 V print 1 U 1 V 1 1. If I write it 8 times for basically 4 points, I will and rewrite everything like this. You're gonna get F1 1, F1 2, 2 F3 3. Basically, I have a non-homogeneous equation. I cannot use the least square to solve it. I have to use SVD, singular value decomposition, to find the F. So if I use the SVD, I can find the F, and remember the side is 0. You cannot use the least square. If I use F, if I use SVD, I will find F, but as I said earlier, the F has rank 2. And what we have here is the F of rank 3, which we have to somehow impose this constraint to the F, so we could get the correct F, because the F that we get right now has rank 3. And if you plot the lines and points, you will get some wrong lines. So how do we impose that? We compute the SVD for F again. I mean, this is another SVD. We use SVD to rewrite the F. The first time we used to find it. The second time we write it to decompose it to U, D, and V transpose. So this matrix is a 3 by 3 matrix, which the value on this diagonal are S, T, and 0 are the eigenvalue of F, and they are sorted like this, descendingly. So R is bigger than S, bigger than T. So we set the T to the 0, and we call this a new D hat, or S. I mean, these are 0 already, and we set these to 0 as well. So we compute the new F with D hat and call them F hat. And this is the F, or the fundamental matrix that we needed. This is a correct one with imposed constraint. Okay. Now how to, as I said earlier, geometrically we visited, we saw that for every point that we had in one camera plane, we had a line for this given point. Here, because we didn't know that this line gonna be here, 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 or here, we actually get a line which is called epipolar line. So here, if you have a look in the equation of fundamental matrix, P transpose F P prime is 0. This is capital P. This is P1, P2, and these are the projection. And here this is L and L prime. Because this, we can write it also for this camera and get the other line here. So if you remember from the first slide, I said we can write the equation of any line in 2D. Like the we can see it as a normal which is perpendicular to this point, and when I say perpendicular to the point, I mean to this ray of light which goes through this point to the optical center. Okay, so PTL is equal to 0 is the equation of the I can see it as the equation of the line. And because these two are equal, I can rewrite it as L equal to FP prime. And basically it says for a given point, I'll given point P prime here, I will have a line, and the this is L prime, this is L. For a given point here, in this camera frame, I will have a line L and the other camera. Also other way around, we could write some L prime is equal FP. So for this given point, here we have a line. This is something we geometrically saw that, and here algebraically we can which is the game. Okay, and the other thing is about the fundamental matrix. Is as I said, it has rank 2. About the epipoles. So as we geometrically again we saw that every point every epipolar line will go through the epipole. So how can we find it? So because this has to be true, P T transpose F P prime, because for every line it will go through that, and it has to be through for every line. So regardless of the point, so this value should be 0. So if I set Fp prime equal to 0, I can find the epipole. So by setting this to the 0, you can find also the epipoles. Yeah, thank you for your attention.